So Vishal is going to talk about some work that we did together. I was involved in it, so I'll tell a bit of the story. This is a project that I guess it started in fall 2019, and then we really picked up when the quarantine started. And we worked really hard, had conversations nearly every day, and then it ended up being a 170-page paper that we posted to the archive. And so Vishal is going to give a glimpse of this today. So take it away, Vishal.
Thanks, Mark. Thanks, everyone, for coming and attending Quilt Day and my talk. So the title of my talk on the abstract list is Geometric Distinguishability Measures Limit Quantum Channel Estimation and Discrimination. And as Mark said, it was a very long paper. So in the interest of time, and since it's a complete topic in itself, I'll only focus on the estimation part of our project. So in this talk, I'm going to first have some preliminaries, then introduce the idea of what's called amortization, which has been used in channel discrimination. And I'm going to generalize that or define that for Fisher information. We will focus on a particular quantum Fisher information called the RLD Fisher information, which I'll define later. So we'll review that, give finiteness conditions for it, which will turn out to be quite important later. And finally, the important contribution, technical contribution, is a proof of something called a chain rule inequality, which helps us prove something called an amortization collapse, which then helps us prove a simple bound for parameter estimation. All of this will definitely become more clear in the next 25 minutes or so. So first, I'll define the problem, which is, let's say we're given n uses of a channel that has a particular parameter embedded in it. This channel can be one of a family of channels, and this particular parameter will say is theta, which is a real number. And since I said we'll be using the channel n times, we want to interact with the channel n times in the most general way possible according to quantum mechanics. And that's what's described by the figure on the bottom of the slide, where we have these S1, S2, so on. These are interleaving channels between the n theta uses. And since they're quantum channels, they encompass any admissible quantum interaction that includes entanglement, as large dimensions as possible, and so on. What we want to do is study the power of these most general quantum protocols to construct what's called an estimator of this parameter theta, which in general in estimation theory is given the notation theta hat, which is the output of this protocol in the figure. So the first disclaimer is that we use something, or we restrict to something that's called an unbiased estimator. This basically means that we assume our estimator is accurate on average. On average, the value of theta hat will converge theta itself. This simplifies mathematical analysis pretty significantly. And we know that informally and both formally in physics, we have this accuracy and precision trade-off. So if we fix that our estimator is accurate, we can focus on the precision. And the figure of merit that's commonly used to measure precision is the variance or the standard deviation, which is just the square root of the variance. And the fundamental mathematical tool in estimation theory is what's called the Cramer-Rao bound, which has its history going back all the way to I think the 1940s. So in the classical case, we don't have quantum channels, but instead we just have probability distributions in which parameters are embedded. And for example, let's consider we have a biased coin. So each flip of that biased coin gives us some samples of a random variable, and we want to construct some protocol that uses those n instances to measure that bias of the coin. And that's one of the simplest classical estimation problems. Those kinds of problems are limited by this first equation on the slide, the classical Cramer-Rao bound, which lower bounds the variance with something called the Fisher information, which is this IF. Again, I'll define that in the coming few slides. What's important to note is that even though we have n instances or n instances of random variable x, the variance can scale no better than 1 over n. And this is understood as a fundamental limitation in statistics, and you can also think of it in terms of the law of large numbers. So instead, if we have, let's say, quantum state family, taking this hierarchy one step further, a very similar bound holds. It's almost the same thing, except the fact that this Fisher information has to be defined in a more involved way to connect back to the classical case. What's probably, arguably, the holy grail of quantum estimation theory is the search for this thing called Heisenberg scaling. So if you look at the equation in the box, you can see that the lower bound has an n squared rather than an n that was on the previous slide. And this means, or this implies that in certain cases, when we have parameters embedded in channels rather than states, it is possible to get this super classical scaling. And the big question that many people ask that we also are interested in is, given a particular estimation task that is given a channel family, can we get Heisenberg scaling? To attack this, first we'll just review some of the technical aspects and move on to some things that we define. So on top of this slide, I have what's called the Fisher information in the classical setting. That is, it's a function of a parameter and a probability distribution family. And in words, I can just say it's the expected value of what's called the logarithmic derivative squared. And again, qualitatively, if I want to construct quantum generalizations of this that can apply to state or channel families, we need to construct non-commutative generalizations of the logarithmic derivative. Now, this is a non-trivial task, mainly because of the fact that quantum mechanics is non-commutative, and the logarithmic derivative, therefore, is not a scalar, not a number, it's actually an operator, and there's an infinite number of them. Two of them that are the most popular, or maybe the most studied, are called the SLD and the RLD operators. The SLD refers to the symmetric logarithmic derivative, which is usually given by the letter L. It's defined implicitly via this differential equation. And you can understand why it's called symmetric, since it involves this anti-commutator between L theta and rho theta. The right logarithmic derivative is defined by a arguably simpler differential equation where you just append this r theta to rho theta. The interesting thing, or the requirement for these quantum logarithmic derivative operators, is that in the classical case, that is, in the case of everything being diagonal, they should reduce to the classical logarithmic derivative. Now, our idea, which I'm going to explain extremely briefly and perhaps not even satisfactorily, is to use this inequality from quantum information theory that's on top, connecting the fidelity between quantum states and something called the geometric Rényi relative entropy. I'm not even going to define this Rényi relative entropy in the interest of time. All that I guess I want to impress on you is that the Fisher information is connected to the fidelity. So using this bound, we're able to get upper bounds on this SLD Fisher information. In itself, this might not be impressive at all, but what we show is that this upper bound is basically the RLD Fisher information itself, and this connection enabled us to perform many of the technical steps that we needed to prove the theorems we proved. So let's move on to the RLD Fisher information, which is what we will focus on entirely. And it's given by this formula for a state family. Again, I mentioned that I would give you finiteness conditions. So this condition on top, this support condition, is the condition that needs to be met for this RLD quantity to be finite. If it's not met, then this RLD quantity is infinite, and it's actually not even useful in estimation theory anymore. The RLD Fisher information is also the largest quantum Fisher information, and in some sense, quite informally speaking, the most classical, or the one that resembles the classical Fisher information the most. And as I said in the previous slide of where we had this idea, we also found out that the RLD Fisher information is very much related to this limit formula with the geometric Rényi relative entropy. I'm not going to use that limit formula or the connection in the next few slides. It's just probably to give you a feel for how we went about to decide what the next step of this project would be. A natural next step when we define the RLD Fisher information for states, the natural next step is to define it for channel families. So a very basic tool that we use almost all the time in quantum information is called the Choi operator or the Choi state. And for a channel going from A to B, the Choi operator is a bipartite quantum state on systems R and B, where you're just passing one half of what's called the maximally entangled vector through the channel. And that gives rise to this very elegant formula for the RLD Fisher information of a quantum channel family. That's a lot of words, sorry. What's most interesting is that usually when you go from a quantity that's defined for states to a quantity that's defined for channels, you optimize over all input states to that channel. However, in this case, for the RLD Fisher information, we find that that maximization isn't even required. We can just stick to this maximally entangled state or maximally entangled vector. And that's what makes this quantity very easy to manipulate, very easy to work with, because there's no explicit optimization in this definition. Next, what follows here is original work that we came up with completely. And it's called the amortized Fisher information. Amortization's dictionary definition is that you're trying to separate out the cost of something into various steps, or you're trying to take it into account in a particular way, which is what we're doing. We're trying to see if we can add some additional resource to the protocol, and we want to see how much benefit that provides to the protocol itself. It's not very easy for me to explain, so I've constructed this kind of crude diagram where if you look at the left, we have a state family that has an input state. We have a channel that has an input state on systems AR, and that input state doesn't depend on the parameter theta at all. The theta influences only n theta. And the output state we get on RB depends on theta only via n theta. However, if we use what's called a catalyst input state, so that means that the theta value not only influences n theta, it also influences the state on systems AR, then the output state is something more, in the sense that the output state will have an increased dependence on this theta. And if I go back to the definition of amortized Fisher information, what we're seeing is that we're focusing on the situation on the right in that figure, where we're including a catalyst, which is this rho theta. However, we're not letting us use that catalyst for free. We're actually taking that into account and subtracting off its cost. So it means, can a catalyst improve performance of the channel itself? Now, the amortized Fisher information obeys a basic inequality that's on top, and this is basically just by definition. What's non-trivial is that can we construct the inequality going the reverse way, as we try to do in information theory quite often. And if we can construct or somehow find that reverse inequality, we get an equality, which is what we call the amortization collapse. And the amortization collapse, it's something nice mathematically, but physically, what does it mean? Or why are we intent on proving it? It basically means that a catalyst cannot increase performance. It means that no matter what, if I go back to this diagram, it means no matter what theta dependence I include in this state, it doesn't help the protocol at all. So we don't even need to consider that. So you can see why it might be something impressive to prove, and it might simplify matters a great deal. What amortization as a concept was introduced for was to basically see the power of what are called sequential strategies versus parallel ones. So the sequential strategy is what I showed about 5 minutes ago, the most general way of processing a channel. A restrictive way of processing the channel n times is called a parallel strategy. And here you can see that it's all simultaneous, and the output of each channel isn't used adaptively to feed to the input to the next channel and so on, which is what's being done over here. So amortization collapse basically implies that sequential strategies are completely equivalent to parallel ones. And we can focus on this probably simpler to implement experimentally strategy than the sequential one. And how do we prove the amortization collapse? We prove it by proving something called a chain rule. And the chain rule is an inequality that looks like the one in the box. It's somewhat involved to prove in a technical way. So I'm just stating it. And what it means is it actually resembles amortization itself. It means we have the chain rule can be recast in this form. If we optimize over input states on the left-hand side, we get this inequality, which is exactly the reverse inequality we desired for the amortization collapse, and therefore we have the amortization collapse. Finally, we want to put these steps together. So I just showed you how the chain rule, that's the first line on this in this box, leads to the amortization collapse. And next, our probably most important contribution is to show that the amortization collapse leads to this Cramer-Rao bound, which is basically this fundamental lower bound on the variance of an estimator. What's really interesting here is that even though I said earlier that Heisenberg scaling might be possible if a parameter is embedded in a channel, we get that the variance, I'm sorry, just let me start that again. So earlier we said that Heisenberg scaling might be possible when a parameter is embedded in a channel. What we get with our result is that Heisenberg scaling is actually impossible by using this chain rule property. There's just one small caveat, which is this all hinges on the fact that the RLD Fisher information is finite. So that's why I earlier said that the finiteness condition will actually play an important role. And the conclusion that we get is that if the RLD Fisher information is finite, then Heisenberg scaling is impossible. And if the RLD Fisher information is infinite, then there's a chance that the Heisenberg scaling might be attained. An interesting qualitative corollary or conclusion we can make is that if the RLD Fisher information, if the channel is a unitary channel, which is the case for a lot of interferometric experiments, then we can obtain Heisenberg scaling because this support condition will not hold. However, any amount of noise that we introduce will corrupt the Heisenberg scaling because it will make, if the noise can make the channel a full rank channel, Heisenberg scaling becomes impossible. So I just want to summarize and conclude that we defined the amortized Fisher information, and we used that to study the power of sequential estimation protocols. In essence, we wanted to compare it with parallel protocols. We then proved a chain rule for the RLD Fisher information, which is the next step in order to conclude what we call the amortization collapse. And finally, we use that to get what in information theory we would call a single letter Cramer-Rao bound, and which is exactly the sequence of steps that's in this slide. And finally, that lets us say that if the RLD Fisher information is finite, then Heisenberg scaling is impossible. This again ties into what I said earlier about the RLD Fisher information being close to the most classical, because once it's finite, it means that these estimation protocols kind of resemble the classical estimation protocols, and that they cannot achieve this quantum or this super classical scaling. And that's basically it. We are working on some extensions of this. The obvious one, and the one that we're working on, is how to extend this to estimating multiple parameters simultaneously. And that's something that we have found we can apply similar concepts to. And that should be actually put out on the archive sometime soon, hopefully this week. And that's it. So thank you.
Thanks, Vishal. I think someone was knocking on your door. It might be an emergency, so you might want to check it. I can try to field the questions if there are questions.
Okay, just give me a minute.
Are there questions from anyone? You can use the raise hand feature. I guess this is the unusual aspect of working from home. So maybe I'll just sort of talk to fill in the space. We wrote a long paper. It was about channel discrimination and channel estimation. So there's a whole aspect of the paper that's about discriminating quantum channels. This has applications to something like quantum illumination, and there's been lots of discussions recently about a quantum radar. And so, you know, with quantum illumination, you have a kind of base station where you send out a signal mode and you retain an idler mode, and then you query whether you're trying to figure out whether there's an object present or an object that's, you know, if there's nothing present. You're trying to figure out, you know, which one is the case. And so you can query multiple times, you know, and repeatedly. And the most general thing you can do is what Vishal described in that figure. You can do an adaptive, so I guess Vishal's back. So you can do an adaptive operation to try to figure out which channel is there. And so, you know, we can also use this geometric Rényi relative entropy to provide bounds in various different scenarios of channel discrimination. In channel discrimination, there are at least two settings of interest. One is the Bayesian setting, where you assume there's a prior probability for which channel is chosen. That's less relevant for quantum radar applications. Another setting of interest is where you have, you know, there are two kinds of error probabilities. One is that it's the false alarm probability, where you say that the object is there when it in fact is not. And so something you might want to do in a radar application is minimize, you have a constraint on the false alarm probability, and then you're trying to minimize the misdetection probability subject to the constraint of the false alarm probability. And so we can also give a, you know, bounds on how well you can minimize the misdetection probability using the geometric Rényi relative entropy. So anyway, I hope everything is, there's not an emergency, that everything is
Yeah,
okay.
it's actually okay.
Okay, good. So glad to hear it. So if there are other questions, we do have time. You know,
yeah, I have a question.
Time goes until 9:45.
Yes, I had a question.
Oh,
Yeah.
great. Okay. Go ahead.
Yeah. So, Vishal, so
Oh.
in this protocol, I think what the final result of this circuit that you've drawn is a single.
This one?
Yes, is a single guess of the value of the parameter theta, right, which is supposed to be unknown.
Yeah, that's right.
So is there a similar setting for this problem where the final answer will be a posterior probability instead of just a single outcome? Let's say you'll give me a new probability distribution for the value theta instead of giving me your best guess. Will that be another setting for this problem?
I think, yeah, I think that would be, but yeah.
So is, okay.
I'm not sure what kind of figure of merit you would use to to measure your performance would be in that case, though.
Mm-hmm, mm-hmm. Yeah, yeah. Yeah, in that case, that might relate to the thing that you said, Mark, right? Where you could also decide to work on the assumption that you have a prior for the value of the parameter theta, and then you try to get the posterior.
That's right. Yeah. So actually, I suppose we should clarify. I think maybe Vishal might have said it. I don't know.
Mm-hmm.
But, you know, an open topic is to look at Bayesian parameter estimation of quantum channels. That could be interesting. I think a lot of the techniques that we were using could apply to that setting. So that's something we could consider in future work also.
I see, I see.
We have about 2 minutes left. Cy did have a question. Why don't you go ahead and unmute? Yeah.
Hey, yeah. So just a quick clarification. So two quick clarifications. One is there an example of kind of a non-unitary channel where you can still have attainable Heisenberg limit?
What do you mean by unknown?
Non-unitary, sorry, where you can still hit the Heisenberg limit. So you said unitary channels you can hit the Heisenberg limit because the right logarithmic derivative basically that condition basically falls apart.
Correct. Yeah.
Yeah, but so what's the? I mean, you implied. I mean, or you maybe said it quickly. I didn't catch it.
Yeah.
You implied something about a rank condition on the map. So what's this? I mean, is it valid for unital maps, for spontaneous emission maps? Are there kind of examples which are physically interesting where we expect to basically be able to hit the Heisenberg limit? Like, is there a
right? So basically, the answer to that, like the basic answer, is that we want this support. We have the support condition, derivative of the Choi operator. And one very simple corollary is that if the Choi operator of the channel itself is full rank, then Heisenberg scaling will be impossible, because a full rank channel will always satisfy the support condition. So we haven't. The only example we looked at in the paper was the generalized amplitude damping channel, and that is a full rank channel. So that does not offer Heisenberg scaling. I'm really not sure about the other models you mentioned.
Yeah, Sai, so to kind of help address your question, there was a recent paper of Cizi Zhao and Liang Jiang. They're both, they were at Yale and they've switched to Chicago. They've identified a necessary and sufficient condition for Heisenberg scaling. And, you know, that's a general condition. And I believe in their paper, they have identified channels that are of physical interest for which you can attain the Heisenberg scaling. And unfortunately, I forget which example it's about.
I know the author, I'll look it up. Sorry, can I just ask one super quick question of Vishal? Vishal, you had this difference of fission information somewhere where you were basically taking away this was the amortized cost. So I think of fission information as variances. And so I would not, you know, my first instinct would not be, I've never worked with amortization. My first instinct would not be to basically take the difference of something that looks like variances, right? I mean, in kind of classic statistics, I would add it as like inside a square root, you know, I would do something like root mean square or something like that. So could you just tell me what the motivation is, or how to think about basically why you took away that, you know?
I guess it goes back, at least for us, I think it goes back to the fact that these fission informations are related to those divergences, like the relative entropies. And so I could potentially divide the equation that's currently in the box with, or not this equation, but this comes about by taking the limit of the particular relative entropy, or the second derivative.
I'll just have to work it out for myself. Thanks.
Oh, all right, okay.
Yeah, that's an interesting question. Very briefly, we think of these as information quantities, and then when thinking of it in that way, it's very natural to subtract them or to add them.
Sure.
Okay, we should move on to the next speaker. Thank you, Vishal. So if you could